a 44.89 score on a proof of usefulness benchmark. That number is carrying a lot of weight in the narrative around AI co-founder agents. Here is the architectural question that score cannot answer. What happens to an agent's decision coherence after month 3, when the market has pivoted twice, the cap table has changed, and the original reasoning context is gone? A benchmark score captures episodic task performance. Co-founding a company is a longitudinal adversarial coordination problem. Those two things do not share a design space. Current AI co-founder implementations converge on a common architecture. An LLM reasoning core, GPT-4 class or equivalent, sits behind an orchestration layer that routes tasks, market analysis, investor memo generation, hiring rubrics, technical specification drafting. The agent receives a system prompt defining its co-founder persona, retrieves relevant documents through a vector store using semantic similarity search, executes tool calls against external APIs, and returns structured output. The evaluation harness producing a score like 44.89 runs discrete task sets against this pipeline: competitive analysis, safe note drafting, founder dialogue simulation. Each task is scored, averaged, and weighted into a single usefulness number. The architecture is optimized for task completion fidelity within a controlled session boundary. That is a coherent design choice. The problem is the assumption it makes about time. The flaw is a context horizon problem dressed in startup vocabulary. Every task the agent completes is stateless relative to the next session. The agent does not accumulate a causal model of the company it is co-founding. When the system prompt resets between sessions, the strategic reasoning that produced prior decisions resets with it. A real co-founder carries 18 months of decision debt in working memory, why a specific market segment was deprioritized, what an investor communicated that shaped the roadmap, which technical constraint forced a product trade-off. That accumulated context is what keeps judgment coherent across a pivot. Current implementations treat each session as a fresh query against a document store. Vector similarity retrieval surfaces relevant facts. It does not reconstruct the reasoning chain that produced a decision 3 pivots ago. Under adversarial conditions, a competitor move, a regulatory change, coherence collapses because the causal graph was never built. The 44.89 score measures what single-session benchmarks can measure: task-level output quality, persona consistency within a session boundary, format adherence, and factual grounding. These are meaningful properties. What the evaluation cannot measure is decision coherence across sessions, strategic consistency under context shift, or adversarial robustness when new information contradicts earlier recommendations. Multi-session longitudinal evaluation frameworks, including work from DARPA's ANSR program and academic agent benchmarks like Agent Bench's long horizon task sets, document 30 to 60% coherence degradation when agents operate across session boundaries without persistent state. A high single-session usefulness score is fully compatible with strategic incoherence at month 6. The benchmark and the failure mode are orthogonal. The architectural correction requires separating the reasoning layer from the memory layer in a way current implementations do not. The proposed design adds a persistent causal decision graph beneath the reasoning core, not a flat document store indexed by embedding similarity, but a directed graph where each node records a decision, the assumptions that supported it, the alternatives considered, and the downstream commitments the decision created. Retrieval against this graph is structural, not semantic. You query by causal dependency, asking which current recommendations are contingent on assumption X and what invalidating X cascades into. When a market assumption shifts, the system surfaces which prior decisions remain coherent and which are now orphaned. This pattern is closer to configuration management in a long-duration defense acquisition program than to how current AI agents manage session context. The dependency graph already exists in mature engineering domains. The gap is applying it to strategic reasoning state. The causal graph architecture is not free. Graph traversal before each reasoning step adds 200 to 800 milliseconds of inference latency depending on graph depth, acceptable for asynchronous strategic planning, problematic for real-time dialogue. A well-instrumented decision graph for an 18-month company accumulates thousands of nodes with relationship metadata, putting storage requirements in the 10 to 50 gigabyte range. Invalidation propagation under rapid pivot conditions is computationally expensive precisely when the system is under the most pressure to respond quickly. The graph also becomes an interpretability liability. Auditing why the agent produced a recommendation now requires traversing a dependency tree that most non-technical founders will not engage with. You trade episodic task throughput for longitudinal coherence. The costs are real. They are also the honest price of a system that does what the benchmark implies it can do. A 44.89 proof of usefulness score tells you the agent can complete a task in a controlled evaluation. It does not tell you whether the agent can remain a coherent strategic partner across the time horizon, where companies actually succeed or fail. The benchmark measures the snapshot. The architecture has to carry the weight of the interval. Those are different engineering problems requiring different designs. Shipping the snapshot score without addressing the interval architecture is not a proof of usefulness. It is a proof of concept.